Welcome back to Pratik Academy. In last video, we have obtained solution for overdamped system, and we have shown that overdamped systems are not actually vibrating systems. In this video, we will obtain solution for critical damped vibrating system and underdamped vibrating systems. Okay. So what is critical damped vibrating systems? When C, it is damping coefficient, is equal to Cc, then system is called as a critical damped system. And for critical damped system, we have zeta is equal to 1. Okay. Now again we have obtained S1 and S2 as S1 is equal to minus zeta plus under root zeta square minus 1 into omega n, and S2 is minus zeta, here minus under root zeta square minus 1 into omega n. Okay. Now here we have zeta is equal to 1, so putting zeta is equal to 1, we get here 1 minus 1 0, so it is minus omega n. Here again minus 1 0 here, so minus omega n. So S1 and S2 becomes minus omega n. So case is here, roots are real, but roots are real and roots are equal. Okay, so we know that for linear differential equations, when roots are real and equal, solution is given by x is equal to c1 plus c2 into t e raised to s t. So this is the nature of solution when roots are real and unequal. Okay. Now putting value of s in equation, we get solution as a c1 plus c2 e raised to minus omega n t. Now again applying same boundary conditions to calculate constant c1 and c2, that is we are assuming that system starts its vibration from extreme end. That means at time t is equal to 0, displacement of system is equal to x naught, that is amplitude or initial amplitude of damped system, and at t is equal to 0, velocity of system is 0. So again directly putting value of boundary condition for displacement in equation f, we get here x naught is equal to c1 plus c2 into 0, so it becomes 0, and e raised to 0 is 1, so value of c1 is coming x naught or x0. Okay, now again second boundary condition is for velocity, so differentiating equation f with respect to time, we get here x dot plus this derivative is in form derivative of u plus u into v, so u into derivative of v plus v into derivative of u in this nature. So applying same, we get derivative of c1 0, derivative of c2 t is c2 into term e raised to minus omega n t, plus for next this term remain as it is, and for here derivative of e raised to at is a into e raised to t, so minus omega n e raised to minus omega n into t. So this is the derivative. And now putting boundary conditions for velocity here, we get 0 is equal to here e raised to minus omega n t, at t is equal to 0 becomes 1, so c2 into 1 plus here c1, this term becomes 0, so minus omega n to 1, so c2 is equal to omega n cn. Putting value of c1 here, we get c2 is equal to omega n into x0. So our solution becomes x is equal to x naught plus x0 or x naught omega n e raised to minus omega n t. Here again for given system, initial displacement or amplitude is same, omega n is constant, so this term is constant, and this term as t increases e raised to negative power is increases, so this term is continuously goes on decreasing. So after giving some initial amplitude x naught, when we release system, it will continuously decreases. Okay, and finally after some time it maintained equilibrium position, but it not crossing equilibrium position, or it is not moving about equilibrium, so it is not a vibrating system. So overtime systems and critical time systems are not actually vibrating systems. Now next is underdamped critical system. So for underdamped critical systems, we know that value of zeta is less than 1. Okay, then again we have s1 and s2 value as minus zeta plus under root zeta square minus 1 omega n. Again here minus zeta minus under root zeta square minus 1 into omega n. Now here, as zeta is less than 1, the term under square root this becomes negative. Okay, and we know that root of square of any real number is positive, or under root if if it comes any negative number, then it is not a real number. So we have to consider, or we for that we take minus 1 as the outside, so it becomes s1 is equal to minus zeta plus under root minus 1 into bracket 1 minus zeta square into omega n here, and s2 is equal to minus zeta minus under root minus 1, we have taken common inside 1 minus zeta square. Now this term as zeta is less than 1, this term becomes real, this term becomes real, and we know that under root minus 1 or root of minus 1 is value of I, that is imaginary number. So our equation becomes s1 is equal to minus zeta. For this root we replace I into under root 1 minus zeta square omega n, and s2 is equal to minus zeta minus I under root 1 minus zeta square. So this number is having one real part zeta and one imaginary part. So this is complex roots, that means solution is having complex roots. And now comparing complex number or real part and imaginary part of complex number with alpha plus ib, then here for this s1 we have alpha 1 is equal to minus zeta into omega n, beta 1 is equal to under root 1 minus zeta square into omega n. Now for alpha 2 we have minus zeta omega n, and beta 2 is minus under root 1 minus zeta square into omega n. So these are the values of alpha 1, beta 1, alpha 2, beta 2. As here roots are complex, solution of linear differential equation will be in form x is equal to a raised to alpha 1 t into bracket c1 cos beta 1 t plus c2 sin beta 1 t plus a raised to alpha 2 t c3 cos beta 2 t plus c4 sin beta 2 t. So this is the form of solution when roots are complex numbers. Okay. Now putting values of alpha 1, beta 1, alpha 2, beta 2 here, we get equation as in this form. Now next step is to collect common terms of cos and sin. So here cos, here this term includes cos, this term includes cos, so we take e raised to minus zeta omega n t as outside into bracket c1 plus this c3 into c1 plus c3 here, c1 plus c3 cos under root 1 minus zeta square omega n t plus c2 minus C4 sine under root 1 minus zeta square omega n t. Now as C1 and C3 both are constant, we are introducing a new constant a for these two. Again here C2 and C4 is constant, we are again introducing new constant p here. Now our equation becomes x is equal to e raised to minus zeta omega n t into bracket a cos under root 1 minus zeta square omega n t plus b sin under root 1 minus zeta square omega n t. For these term we can either replace it by in terms of sine or in terms of cos, because we are having two relations, sine a plus b and cos a plus b. Sine a plus b is sine a cos b plus minus cos a sin b, and cos a plus minus b is cos a cos b plus minus sin a sin b. So using these relations we can replace this equation or this term in form of either sine or either cos. So considering sine part, here equation is x e raised to minus zeta omega n t into bracket a1 sine under root 1 minus zeta square omega n t plus phi 1. Okay. Now so here in this equation a1 e raised to minus zeta omega n t sine into bracket under root 1 minus zeta square omega n t plus phi. So here if we compare this equation with previous two equations, we find that in previous two equations there is no any periodic function, but here we are having sine as a periodic function. So here our displacement is crossing our equilibrium position because it is working on sine function, so it must or it crosses equilibrium position. Again here a1 is constant, zeta is constant, omega n is constant, and t is increases with time. So power of e in negative side will continuously goes on increasing with increasing time. That means this term, that is amplitude of vibrating system, is continuously goes on decreasing, and it is forming periodic motion about equilibrium position. So here we see that this amplitude of each cycle is continuously goes on decreasing, and as it is working on periodic function, it is crossing equilibrium position. So our underdamped systems are vibrating systems. Underdamped systems are vibrating systems, and if we compare this system with our standard SHM equation, then x is equal to a sin omega t plus phi, where phi is the phase difference, omega d is a damped frequency, and a is amplitude. If you compare corresponding terms, then amplitude of damped system AD is equal to a1 e raised to minus zeta omega n t, and frequency of damped system is omega d is equal to under root 1 minus zeta square into omega n. So this is about underdamped vibrating systems. So in previous lecture and this lecture we have seen different damped systems, that is overdamped system, critical damped system, and underdamped systems, out of which only underdamped system is a vibrating system because it crosses mean position, and in case of overdamped system and underdamped systems, these are not actually vibrating systems because they are not crossing equilibrium positions. So if you like this video, please share with your friends, comment on this video, and thank you for watching.